we're going to look at some graphs that you already know. For example, x minus 1 squared is a parabola moved 1 to the right. If you wanted to find its y-intercept, so if I had x minus 1 squared, y-intercept, I'd plug in 0 for x. 0 minus 1 is negative 1, negative 1 squared. The y-intercept is at 1, so I would have that point. And it's already factored, so if I plug in 0 for y, x minus 1 squared is x minus 1, already factored. I would just get x equals 1 as the only x-intercept. And because it's a parabola with a positive leading coefficient, I know that my end behavior has to do this. Well, the only way that works is if we get a bounce here. It has to bounce off the x-intercept, because if you go through, you have to come back up again, which would introduce another x-intercept, which doesn't exist. The whole idea of using the y-intercepts and x-intercepts is you find them all, and if you found them all, you can't introduce a new one. That would be wrong. So if we went through this x-intercept, the only way our end behavior would be going back up is if we had another x-intercept, which would be wrong. So the only way that this works is if at this x-intercept it bounces. And so we're going to notice something. Do you notice that the x-intercept happened twice? And this is called multiplicity. When you have an x-intercept happen more than once, it has a multiplicity. In this case, a multiplicity of 2, because it happened twice. And off to the side, we'll write the following note. That if you get a multiplicity that is even, wow, I did not spell that even close to right. Multiplicity. Whew. If you have a multiplicity that's even, something that happens twice, or 4 times, or 6 times, or 8 times, etc., now, I'm putting bounce in quotation marks because it's not a mathematical word, it's just a describing word to describe that what happens at the x-intercept. And we can see this easily in a graph that we already knew, which was our parabola. Now we can do the same thing x minus 1 cubed really means x minus 1, x minus 1, x minus 1. But from your transformations unit, does it make sense that this is just an x cubed graph moved 1 to the right? Its x-intercept is at 1. Its y-intercept, if you plugged in 0, and it would have a leading coefficient x cubed, which is positive, acts like a line. There's our end behavior starting down there and ending up there. But if I just went straight through that point, it would look exactly like a line. But this is an x cubed graph. And what happens when the multiplicity is odd and bigger than 1? Okay? So we're going to make actually 2 notes here. We've already seen odd multiplicity of 1. That's what happened in all of our previous examples. If the odd multiplicity of 1, your graph went straight through that x-intercept. That's what we had in our previous example right here. Right? It went straight through this x-intercept, straight through this x-intercept, straight through this x-intercept, and straight through this x-intercept. Because each of these happened once. That's considered, it's kind of not not the right word saying multiplicity of 1, because multiplicity sounds like it happens more than once, and it only happens once, but it's sort of a unique situation. If it only happens once, it goes straight through. But if you have an odd multiplicity bigger than 1, and I'm going to write like 3, 5, 7, dot, dot, dot. If the multiplicity happens like that, the graph, here's our bends is a good word, or I really like this wording. It bends or flattens out at the x-intercept. In fact, the flattening out means that if you would draw a flat line there, the graph almost gets completely flat at that one point, which if you draw your x cubed graphs, they should get really flat. A tangent graph, which is kind of like x cubed, doesn't get flat. They're a little bit different that way too. Again, you'll see that more and have it explained more once you take calculus next year. Sorry, I'll move it down so you can see it again. So we say that if the odd multiplicity is 3, 5, 7, and so on, the graph bends or flattens out at that point. So if I was drawing this, here I have x equals 1, x equals 1, x equals 1 happening 3 times. So I would have a multiplicity of 1. To really show that, I would draw a little tiny flat line, and then I would have my graph go into the flat line there and then come out of the flat line. I'll automatically get a bend. If I draw a tiny little flat line and I go through it, I will automatically force my graph to bend. Okay? Because if you go straight through that point, it's a 1-mark mistake because it's an idea that we're learning in our course. So anytime we make a mistake in the math of an idea that's like new in grade 12, those are always considered concept errors, and they always get 1 mark taken off on the exam. So drawing that little flat line really helps us. So now we're ready with these ideas to graph example 3. And what's really nice about example 3 is they've already factored it for us. Okay, this would be harder if you had to factor it completely, but it's already factored for us. Now, if it's already factored, it's a little bit harder to see, not super hard, but a little bit harder to see what kind of graph did this start with. Was this an x cubed graph, an x to the 4 graph, an x to the 5 graph? What would it have been? Okay. F of x, if you multiplied it out, you would get an x to the 5 graph plus dot, dot, dot. How do I see that? Well, if I wrote out f of x as x plus 1, this is a little bit annoying, but I'll write out all 4 of them, because that's what that 4 means, right? If I wrote that all out, does it make sense that your first ones are all x's? And if you multiplied all of your first ones together, you would get a 1x to the 5. And that 1 is positive, so our end behavior acts like a line. There's our end behavior. Also, when it's in factored form, your y-intercept is a little bit harder to find. You still plug in 0 for x. But now when you plug in 0 for x, can you see that this is going to be positive 1 to the exponent of 4 times by a negative 2. It's going to be negative 2. A little bit harder to find the y-intercept because you have to do a little bit of mental math. Not crazy, but you can't, like, sometimes people just take the last number and by coincidence it works here. Oh my goodness. No, it doesn't by coincidence work out to be negative 3 in the second one. So we do have to try that a little bit. And then our x-intercepts, are going to be at -1, 0, and I'm going to put underneath this one, that has a multiplicity of 4, and 2, 0, from that factor, this one has a multiplicity of 1. On our points, we've got our y-intercept at 0, -2. We've got x-intercept at -1, 0, and another x-intercept at 2, 0. And our end behavior, we know it has to start down here and end top right. Okay? Multiplicity of 4 underneath this one, I'm going to write the word bounce. And multiplicity of 1, I'm going to write straight through. Just to remind myself what has to happen at those. Can I draw a nice smooth curve through all of those points following these rules starting down here? Okay? The bounce has to be nice and round, straight through. Looks like that. Notice how you might be tempted to hit this point and go up right away. It's like human nature to want, when you have a point, you're like, that must be my lowest point. It doesn't necessarily have to be your lowest point. If while drawing the smooth curve, it feels awkward to make it go up right away, it most likely means that it probably went down lower and then up after that. But again, you're not going to get marked on knowing where the minimum is. That's calculus's job next year. Calculus says we have a really easy way to find that point for you. You just have to learn derivatives. No problem. So here's the sketch of our graph. When we go to part B, it's already factored for us if you wanted to find your y-intercept. And sometimes you're going to want to actually show the math. So y equals negative. Plug in the 0. So we have 0 plus 1 to the 3. And then 0 minus 3. This negative is like a -1. Do each one separately. 1 to the 3 is 1, and 0 minus 3 is -3. It's not hard mental math, but you should see how many students just think they can do this all in their head, and they do a really good job of doing it all in their head wrong. It happens. It's so easy to make a mental math mistake with negatives. So an interim step, just figure out each bracket separately, and if you have a negative out in front, it's still a -1. And then put it together. Our y-intercept is at 3, 0, 3. If you get your y-intercept wrong, and you try to follow all the rules, nothing's going to work. So if you're trying to draw your smooth curve with bounces and bends, and it's not going through the right points, and you have to invent a new x-intercept to make it work, you know you've made a mistake. So double check some of your math. So now for your x-intercepts, since it's already factored, can you see that one x-intercept is going to be at -1? And this one has a multiplicity of 3. Cool, I was going to write flattened out, but bends is less to write. That's why my B has that little F top to it. Okay? And the other one was at 3, 0. Multiplicity of 1. This one's going to go straight through. So when I go to graph this, I'll just do it here on the side. We had our y-intercept at 0, 3. We have x-intercept at -1. And since the bend flattened out, I'm going to just draw a little straight line there already to remind myself. Okay? And at 3, straight through. So that one can just be a dot. We didn't figure out the end behavior for this one yet. Okay? This one too, just do it up here, g of x equals negative x plus 1, x plus 1, x plus 1, x minus 3. Here are all my first terms. Can you see that you're going to have an x to the 4? But with that negative out in front, it would be a negative x to the 4. So my end behavior starts at the bottom, ends at the bottom. So I go to my graph. I start at the bottom. When you're drawing it, go to the one flat part. Go through your flat part and then go up. I think it makes sense to go higher and then go straight through the next one. If you draw that little flat line, you will naturally get that bend. And drawing that flat line is important because in calculus, you're going to learn about tangent lines. Tangent lines, for example, at the maximum point right here, the tangent line is a line that touches that point and only that point. That tangent line would be perfectly flat. If I drew a tangent line at this x-intercept, it would touch it only once. It would have a negative slope. At the point that flattens out, the tangent line would be flat as well. So that's one of the reasons we flatten it out. Because we're going to find out next year in calculus that the tangent line flattens at that point. So the multiplicity tells us what's happening at that x-intercept. Most of the time they go straight through, but some of the times they bounce and some of the times they bend. And the bouncing and the bending makes it work so that your end behavior still matches up in the end. Questions for practice on this one? 9, 10, 11, and 12.